Here's a section on the chi-square distribution and tests of independence. I think it's a good idea if we just start this by looking at an example, and then we'll get in more detail. This table shows the Myers-Briggs personality preferences. Okay, here's the personality preferences, apparently. Extroverted and introverted for a random sample of 406 people listed by professions. Okay, so we've got personality types, extroverted, introverted, and their professions: clergy, MD, lawyer. These are just occupations and column totals and totals, row totals. And then what we're asked to do here is use the chi-square test to determine if the listed occupations and personality preferences are independent at 0.05. And two events, you may remember, are independent if they have no relationship to each other at all. So I think what we're being asked here is to determine if personality preferences, if you're an extrovert or an introvert, and your occupation have nothing to do with each other. If you know somebody's occupation, you don't know their personality type. If you know their personality type, you can't say anything, make any prediction about their occupation. This table here in this problem, this is an example of a contingency table. I've drawn one down here. So what do we have in here? We've got rows and columns, all right? So in this one, I've got one row, two rows. So I've got two rows and actually two columns. These are just totals. This last column is just totals, and this last row are just totals. So really, the table is right here. I've got rows and columns, and each row and column I've got observed frequencies and expected frequencies. I wrote a definition of a contingency table here. A contingency table is an arrangement in which a set of objects, now the set of objects in this problem right here are people, in which a set of objects is classified according to two criteria, one being entered in rows and one in columns. All right, so our collection of objects are people, and the criteria that we're using are occupations and personality types. And what's nice about a contingency table is that it can show us a picture of the interaction between two variables. So we're able to see if there's any interaction at all between occupation and personality type. And our interest is this. We're interested in determining if a relationship exists between those two criteria or if they're independent. So our H0 is different than before, right? Usually we had numbers in here, but now it's different. It's just going to say this. The two criteria are independent. H sub A will say they are not independent. And I'm not going to write in the actual problem two criteria. I'll write exactly what they are. So I might, in this example, I might write occupation and personality type are independent. So we're going to build a contingency table, and as we do, we will include both the observed frequencies and expected frequencies. So I'll just go back to my drawing back here. If I look at my table here, I'm going to have in each row and column, I'm going to have observed frequencies and expected frequencies. And then we want to measure the discrepancy between the observed values and the expected values. We're going to use this chi-square statistic to measure the discrepancy between what we observe and what we expect. Now let's just go back to this problem for a minute here. The observed values, those are always going to have to be given, right? Because, we're not actually going out and doing this ourselves. So in the textbook, they give us problems, and the problems will always give us the observed values. We have to come up with the expected. So they're giving us observed, all right? They're going to give us these. We have to come up with expected frequencies. Then we'll use chi-square to measure the difference between what we observe and what we expect. And here's how we're going to get our expected values into each one of these cells. We're going to take the row total, multiply it by the column total. So you take the total in that row times the total in that column and divide it by the grand total. And the grand total, well, that just turns out to be the sample size. That's what we mean. And because it's a chi-square, we need degrees of freedom. And degrees of freedom is just going to be the number of rows that you have times the number of columns that you have. So I'm building one of these contingency tables, so I've got, okay, I'm just like building this table right here. I'm just going to write this, except I'm going to expand each one of these cells here, because in each cell I have to put not only the observed frequencies, which were given, but I also have to put in the expected frequencies. So it has some writing room. I'm just going to expand all of this. So let's see, we're going to have, all right, so I'll have this. Let's block these off. All right, and then I'm going to block that off and this. Now, what I'm going to do here is I'm going to divide each of these cells up. So what I'm going to do is on this side over here, on the left side of the cell, I'll put the observed frequencies. Those are the ones that are given to us. And then on the right side, I'll put the expected, and I have to compute these. So into the left side, let's put these observed. So it's 62, right? I'm reading right out of here. 62, 68, 56 if I go down. So it's 62, 68, 56. And then preference for introverts is going to be, what, reading straight down, 45, 94, 81. So 45, 94, 81, and they give us the totals, right? The totals are given. If you add down this row, apparently you get 186. We could check that. And 220 over here. In the rows, or this column here, it's going to be 107, 162, 137. Now, if you add across this bottom row and add along the bottom row or add down this column, we should get the sample size. That should come out to 406. To get the expected frequencies, I'll use this little formula that we have here. Row total times the column total divided by the grand total, or the sample size. So how about if we do this? So E 1, 1. Now this is going to be just a notation for, this will be row 1, column 1, or just like matrix notation, row 1, column 1. So E11, this is going to be the total in row 1, right? The total in row 1, now you can just read it right across, right? The total in row 1, 107. So this becomes 107 times what? E11, the column total, so I'm in column 1. There is column 1 right there. That's a 186. Divided by the grand total. And the grand total, that's the one down here. If you add up all the row and all the column, you get 406. That's our sample size. 406. And I got 49.0197 and so on. I'm going to round this off just to 49.02. So let's say 49.02. Now maybe I'll get the expected value in row 1, column 2, right? Row 1, column 2. So I'm going to use row 1, column 2. All right, so we'll get these totals in. We'll get row 1, total in row 1 is 107, times the total in column 2. Now column 2, that's this one here, that's a 220, divided by that grand total, 406. And I am getting 57.98. So I've got that first row taken care of. Let's go to the second row. All right, second row, first column, right? Expected value in the second row, first column. So this is going to be our total in the second row. Now the total in the second row, all right, total in the second row is right here, 162. I'm in row 2, second row, so 162 times the total in the first column. Now the total in the first column, there's the first column, 186, divided by our grand total, which again is 406. And that is giving me 74.22. Well, I went ahead and filled a few of these in here, but let's get the last one, just so we're sure we can do this. So the last one is going to be, now where are we? We're in the total in row 3, column 2. All right, so the total in row 3. All right, here's row 3 right here. That's a 137. All right, so that's a 137 times, now times what? Times the total in column 2. Column 2 is this column right here, so that's 220. And that's all to be divided by the grand total, 406. And I'm getting 74.24, just rounding off. Now we've computed all 6 of those expected values. Let's put them into our table. So right here, what is this one going to be? This is the expected value in row 1, column 1. So the expected value, frequency in row 1, column 1, that was a 49.02. Let's put that in. 49.02. And then what goes here? This is row 1, column 2. That's our computation here. Row 1, column 2 is 57.98. And then second row, first column. Okay, second row, first column. Second row, first column is 74.22. So that'll be a 74.22. Then second row, second column. Second row, second column is 87.78. 87.78. Then third row, first column, 62.76. 62.76. And then third row, second column is 74.24, right? Third, second, 74.24. 74.24. With all that computation, we're now ready to apply our chi-square statistic, which is, right, we're going to add up what? We're going to add up these O minus E's squared divided by E's. All right, here's the first one. So we've got what? We've got 6 of them. We've got this O minus E, this O minus E, O minus E, O minus E. All right, let's do them for each one. So this is going to look like this. It will be, all right, the first O minus E. I'm just going to go across the rows like this. So O is 62. Minus the E, which is 49.02, squared, divided by the E, the 49.02, that's it, plus. Okay, so I've got the first one. There's the first one. Now it says to add. All right, so go to the second one. So I'll just go across the rows here. So this one is going to be O minus E, so 45 minus 57.98, right? O minus E, square it, divide by the E, 57.98. Now, I'm just going to write these next ones down, and then we'll add them up together. We've got our computed value, 8.65. We need to get our critical value, so we're going to look at the chi-square table with what degrees of freedom? Well, degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So 3 rows minus 1, 2 columns minus 1. So we're going to have 2 degrees of freedom, and we're running this at 0.05 according to the problem. So we'll come over to our table, we'll look for 2 degrees of freedom, Keep going to the O5 column. There it is right there. So it looks like the critical value is 5.99. All right, so our critical value here, I'll write it down here, 5.99. And if I draw my picture, right, it's chi-square. So chi-square looks like this. Goes up quickly, slides down to the right. It's always a right tail test. So that area is 0.05, and our critical value here is 5.99. Our computed value is, all right, that's the 8.65. So here's 0. Here's 5.99. 8.65 is out here in the shaded region. All right, that's our 8.65. So we're in the shaded region. Now the way I remember this is this. I'm in the shaded region. Shaded starts with S. So does significance. So we have significance here. So there's a significant difference between the observed and expected values. So we are going to reject H naught. Now H naught, remember, was the claim that these two criteria are independent. So H naught states that occupation and personality preference are independent. The alternate hypothesis, if they're not independent, we are rejecting H naught. We're rejecting this. This says that they are independent. We're going with this one. They're not independent. So let's write the conclusion. At alpha equals 0.05, this sample indicates that occupation and personality preference are not independent. This really is one heck of a lot of work, a lot of arithmetic computations. We can get around this if we use our TI-84s. Let's give it out a try. We're going to use the matrix feature on our TI-84. So this picture is really fuzzy. But to get the matrix, what you're going to do is you're going to go to second, and then it doesn't show up too well down here, but it's on the x to the -1 key. It says matrix above it. So press the second key, then the matrix key, x to the -1, and then your screen comes up with this. It says names, math, and edit. Under names, you're going to get a list of all the matrices that you could put into your machine. Under math, let's not worry about that right now. We're going to go over to edit. So go over to edit. So we're going to select edit. Now we can choose any one of these matrices. So why don't we just choose matrix A? So why don't you just select one. All right, select one, and one says matrix A. We'll put all of our entries into matrix A. You can select any one you want, just so we're all together. Select A. Now when you do that, what comes up is it says matrix, it says the name of your matrix, and then it has something by something, right? A little cross for by. What you need to put in is the size of your matrix. Now the matrix we're using is a 3 by 2, right? We have 3 rows, 2 columns. So just press 3, enter, 2, enter. Then what you get is a picture that looks like this. You get 3 rows. Now there may be stuff in there already from the last time the matrix was used, but you just type right over it. So what we're going to type here are our entries. So we're going to type 62, press enter, and then the entry, the cursor, just comes right over to the next line. So row 1, column 1, you press enter, it comes to row 1, column 2, type in 45, press enter, then it drops down to the second row, first column, type in a 68, press enter, cursor moves over to row 2, column 2, we have a 94, these are the observed values that were in our problem. Press enter, cursor goes down to row 3, column 1, which is a 56. So you type in a 56, press enter, and then an 81, and press enter. Now, just to be safe, so nothing else gets entered into your calculator, why don't you press second, and then right next to it is the mode key. That's quit. So it gets you out of that matrix feature and into your computation window. We've got all the things we need in our machine now. All we have to do is have it compute for us. So here's what we're going to do. We're going to go to Stat, over to Tests. Then you have to scroll down or scroll up. Scroll up will get you there faster. But you scroll to item C. So you select C, and C says chi-square test. Now what comes up is observed, expected, and calculate. All right, now where did we put our observed? We put that into matrix A. So if it's not already there, you'll have to go get matrix A. So what you want here is matrix A. So here's how you get there. You're going to press second, and then, down here is that x to the -1 key. It says matrix above it. And then select number 1. Or select matrix A, wherever you happen to put it. All right, so for observed, you want your matrix A. That's where we put our values. To get that matrix, go to second matrix and select matrix A. Press enter. Now when you press enter, by default, matrix B comes up. Now that is where the calculator just did, and I'm going to go back a page, another page, another page. We did all these computations, right? Took us a long time. We had to do all those computations. We had to do all of these. Then we had to do all of these subtractions. Then we had to add them all up. Well, the calculator does all of that work for us. It puts the expected matrix, I'm going to go back again, sorry. It puts all these yellow numbers in, does all those computations, puts all these expected frequencies back into our matrix and just stores them right as matrix B. Now just go to calculate. When you calculate, all right, there's that chi-square value. That was all that work that we did, or chi-square star we call it. That's the 8.6, I'll round off. But here's the one we're concerned with, right? The p-value, I'm getting 0.0132, 0.0132. There's our p-value. So what do? P and alpha, let's compare them. P is 0.0132. Alpha, we were running this one at 0.05. So in this case, P is less than alpha. So do you remember what to do here? If P is less than alpha, you reject H naught. And I'll just paste it in here just to remind us of what we did when we did it the long way. H naught stated that occupation and personality preference are independent. The alternate hypothesis says they're not independent. We rejected this in favor of this. So we're going to say at alpha equals 0.05, this sample indicates this occupation and personality preference are independent. And that finishes this section. So if you want to do all this by hand, that's fine. I think it's important to at least see it done once so that you know really what's involved, what you're measuring when you see those differences. But we can have the calculator do all that for us, and that's, I think, the way that we prefer to do it.